Hi, I'm David Steelman, and I'm going to be presenting my journal club presentation today. Vegan mycoprotein concentrate from pea processing industry byproduct using edible filamentous fungi. This research was done by Pedro Salza Filho and his associates, who you can see on the side of the screen, and this article was found on Biomed Central. So today I'm going to be going through the abstract of this research. Then I'm going to talk a little bit about the background, what's already known in this field, and then we're going to move on to methods, what they did for the research, followed by results and discussion, and then finally I'll put a little bit of my input into the research. So the abstract for this paper is: currently, there's 1 billion people in the world who are lacking protein in their diet on a daily basis, and the goal of this study is to find a vegan alternative as opposed to raising more livestock, which is extremely harmful to the environment. So seeing how much of the PPB, which is the pea producing byproduct, can be converted by different filamentous fungi, and then tracking the production yield that they produced while in the PPB. And the 5 fungi that were chosen for this study were Aspergillus oryzae, Fusarium venenatum, Monascus purpureus, Neurospora intermedia, and Rhizopus oryzae. Sorry if I butchered any of those names. Okay, so moving on to some of the background of what we know in this area. One, the protein deficiency that's around the world is largely due to the overconsumption of animal protein that goes on in the developed countries of the world. And since they can pay for it, they get it. Poor people are left without the animal protein. And there's a whole multitude of health issues that can come along with having a protein deficiency. Muscle weakness, immune system is weaker, PM, marasmus, the list goes on and on. So this study is looking at these fungi as an alternative to be able to feed these poor people who aren't getting protein. These fungi are currently already being grown and used mostly in Asian cuisines and red yeast rice wine, also in polyunsaturated fat and vitamin supplements recently. And they've got the science down to growing them very well in these synthetic vats with glucose, ammonium, and biotin. However, it's an expensive process, so it ends up that there's a high price point, and all the people who are over-consuming the animal protein are also the only ones who can afford these fungi right now. So this study is looking at what happens if they try to grow these same edible fungi in PPB, which is the pea-producing byproduct. And this is for several reasons. First of all, PPB is widely available. Peas are the second highest produced legume in the world at 17 metric tons, only behind soybeans. And 2, it's really cheap because the PPB is the byproduct. It's essentially waste. It's not being used. It's just being thrown away. All the PPB actually in this research study was donated for free. What you're probably wondering what exactly the PPB is. So in the pea industry, there's 3 things being produced: pea flour, pea protein concentrate, and pea protein isolate. And if you see the whole process there on the screen, you can see 3 streams that are pointing to the box that says fermenter in it. And those things say oligosaccharide containing side stream, insolubles from the mixer tank, and soluble fibers and residual starch that come off in the centrifuging process. All three of these things are combining and being considered the PPB. It's important to note here that this entire schematic here is not outlining the research process that's being done. That's by the pea producing corporations. The research is only that fermenter to the fungal biomass step that you're seeing in the very bottom. And the last thing that I want to address for the background is what are mycoproteins and what are some of the benefits of them. So mycoproteins, that's the class of proteins that they're single cell proteins that all fermenters make. So that's just a general class there. And the benefits of these are, first of all, if you eat enough protein, it's going to prevent all those things that were caused by the protein deficiency that I mentioned earlier. Two, it happens to have cholesterol lowering abilities in addition. And thirdly, it's found to be more satiating than animal protein, which is good for people who aren't getting enough nutrition. And this is due to a different ratio of chitin beta-glucans that are found in these specific proteins. Next part is the methods section. So before anything was actually done, they analyzed the PPB before they even got started. And you can see that there on the side. It's mostly starch. The second highest thing is protein, but it's still not very high in protein. That table is based on dry weight. So PPB is not considered high in nutrients at all. And after they analyzed the PPB, ordered the spores, and they kept them on PDA, potato dextrose agar plates, incubating them for 5 days at 30 degrees Celsius. And after that, until they were ready to start the experiment, stored them at 4 degrees. The first step then from there is when they were ready to take the plates out, put 20 milliliters of distilled water on top of the PDA and scrape with a disposable cell spreader to get some of the spores loose in the liquid, and then take 3 mils of that and transfer it into the YPD broth. So the 3 mils of that solution goes into 100 milliliters of YPD broth. And then that from there gets incubated for 48 hours, and that is what's going to create the dry fungal biomass that they're going to use to incubate at the next step of the process. So the dry fungal biomass is used to inoculate the PPB solution, which is going to be 100 mils of PPB solution with the concentration predetermined, which they did by going to the maximum amount they could put in the solution before it reached retrogradation. And then these are the Erlenmeyer flasks are stored in a water bath shaker at 35 degrees Celsius, and some of these flasks receive beta amylase in addition to the PPB solution, and some are left without. These Erlenmeyer flasks, I forgot to mention that they're all going to have their pHs adjusted to 5.5 by adding 1 molar HCl before they get autoclaved for 48 hours. Then after this happens, they harvest the fungal mycelium that grew, and they dry them out at 70 degrees Celsius. Then they measure the weight of the new biomass. And all along, every hour during this 48-hour period, the whole process, levels are being taken to see how much sugar is being consumed and what metabolites are being produced, so they know how much new protein production is taking place. It's also important to note that all the data that you're going to be seeing later on, they're not single points, they're mean averages. So there's duplicates for all 5 fungi type for both the PPB solute without the beta amylase and with. In the next step, they're taking the fungi mycelium that they've produced and they put it in an airlift bioreactor, and they add cellulose enzyme complex at the beginning of the incubation, and this is going to further the cultivation of the fungi and create more mass. And they continue to take data points, in this case only every 12 hours for the 48 hours, and it's going to be stored at 30 degrees Celsius again. The team did some analysis of the final cultures before they moved on to looking at the results. They looked at the spore concentration, and then they were able to calculate concentrations for acetic acid, ethanol, glucose, glycerol, lactic acid, xylitol, nitrogen, arabinose, galactose, and sucrose. They did this by using an ion exchange column, looking at UV absorbance, and thirdly the refractive index. This part was a little above my head how they calculated it, but they were able to get concentrations. Most importantly, the nitrogen concentrations, because there's a nitrogen to protein conversion factor that's been pretty well established at this point, so this gave them their first general prediction of how much protein was produced in the process. Okay, now on to some of the figures that they posted in the results section. So here this is tracking the amount of glucose that's being seen in the 36-hour period when the PPB solute is being incubated. The triangles don't have the addition of the beta amylase, and the squares do. So you can see the difference with them overlap like that, and each of the, it says below which is which, each box is a different strand of fungi. You see some similar figures here on the left, but in addition for 3 of the strands of fungi, the bottom table B there is also showing the ethanol amounts, not just the glucose. Once again, sugar and ethanol levels shown on these on the right. This time though in the airlift bioreactor, and also it shows the other sugars besides that aren't glucose. So all 3 sets of those tables are to show how well the fungi are metabolizing the PPB throughout each process in each setting. So in the PPB solute with no beta amylase, with beta amylase, and then also in the airlift bioreactor. Okay, these last 2 figures are the really important ones that summarize up all the data. So in this one we see bars for all 5 fungi, the light one being the PPB solute with no beta amylase, the dark one with, and you can see that the dark bar is higher in all 5 cases, so we know that the beta amylase is working. It's helping make the process of making these mycoproteins more efficient. And we see that A. oryza is the highest producing strand in both cases. So for further research, that's going to be the most likely target that they would continue on with this. Okay, this second table, this might look like the same set of statistics just presented in a different fashion at first, but what you notice here is it says protein yield. So in the other, the bar graph, that's biomass yield. So just because something's gaining more biomass doesn't necessarily mean that it's gaining more protein, since they each have different percent protein makeups, which you see in the column next to the protein yield. So in the first subset, even though we see that A. oryza has the highest difference between its bars and biomass of the sample without beta amylase and with, we can see here by the protein yield that N. intermedia has a 0.11 protein yield, which is the same as A. oryza, which is showing what I just said before. So N. intermedia didn't have as much biomass gain, but did have the same amount of protein gain. With the beta amylase, though, A. oryza does come out as the most efficient fungi for making new mycoprotein, not only in terms of biomass, but in actual protein mass as well, with 0.14. They have no table or figure that shows these same numbers organized for after they're put in the airlift bioreactor, but it is linear, so these numbers are going to get multiplied, but by the same amount. And A. oryza, which is the top one, ends up climbing up to 0.26 protein yield gram compared to gram of the PPB that was put in. So a couple things to discuss about the results that we saw. So what the results tell us is that with A. oryza, the max results we're going to end up getting is for every ton of PPB that we use in this process, we could make 260 kilograms of pure protein. This number is going to be a little different because, one, for safety reasons, due to high RNA content, this protein is going to have to be treated with heat to destroy them, which is also going to take some of the protein along with it. Also, as we saw in the figure that showed the glucose levels when in the airlift bioreactor, that the full metabolism didn't take place in the 44 hours. So had that process been carried out longer, the number probably would have been even higher than 0.26. So with that being considered, that number probably making it higher, but the treatment of heat making it lower, it's hard to say whether the number would be slightly above 0.26 or below. Another thing to note for the safety is they monitor the concentrations of the different sugars and starches, nitrogen, whatnot throughout the process very tightly. But one thing they didn't look at was mycotoxins that can be harmful throughout these processes. So if this were actually to be installed, they'd have to be mindful of that as well. Finally, the conclusion. So the main finding of this is that PPB is indeed a very effective medium for growth of edible fungi, and the fungi that they're forming are extremely dense with protein. Up to 54% of their biomass is coming in protein. They also found ways that are making it what works and what doesn't. So they found A. oryza, that's the best fungi to be using in the future. 2. Beta amylase does increase the production, as well as using the airlift bioreactor. So this study can't say for sure that this is going to be beneficial, but these numbers do, they think, indicate that if they can find a healthy way of doing this, monitoring the myotoxins and the RNA levels after they've been produced, that this is most likely cost efficient enough to be incorporated in already running PPI facilities. Finally, I just have a couple things that I want to say that I myself noticed about this research paper as I was reading through. One big one is everywhere in this entire paper, it says that things are being done in duplicates. So the PPB saw you with and without beta amylase in the airlift bioreactor. It says these are being done for each fungi in duplicates. And that's, we don't know if that's 2 samples, 100, whatever. So later when you're looking at you know, the data in those figures, which are all mean averages, you don't know how much weight to put in them because you don't know how many data points are behind them to support it. My second thing that I want to say is there's no cost analysis done in this paper whatsoever. So in the beginning, I talked about how these fungi are already being grown in mediums with biotin, ammonium, and glucose synthetic mediums, and that it's really expensive to do that. And while we know that PPB is very, very cheap, there's other things being used, not just that in this experiment. There's the PDA plates, the YTD broth, the cellulose enzyme complex that they add when it's in the airlift bioreactor. These all have their own costs, as well as, using the machines themselves, and there's no analysis of, is this cheaper? How much cheaper is this? That sort of thing. Because ultimately, if it's not cheaper, enough cheaper, we're going to be stuck with the same problem where we're growing these fungi, but we can't get it to the people who really need the access to it, those who aren't getting enough protein. So that's the end of my presentation. I hope you guys enjoyed it, learned something. I think there's supposed to be a time for questions. I'm not exactly sure how that's going to work. If you just write them down, give them to Waterman, and they'll get to me and I get back, or what. I think the paper itself will also be up on Moodle, so you can read for yourself also if you want to find out any more about this.